The 946 eruption of Paektu Mountain on the boundaries of China, Korea, was one of the most powerful in recorded history and is classified as a VEI 7 event. The eruption resulted in a brief period of significant climate change in China. The age of eruption has not been well constrained, but a possible date is A.D. 946. The 946 eruption of Paektu Mountain has been dubbed the Millennium Eruption, or the Tianqi Eruption, and erupted about 100 to 120 cubic kilometers tephra. The eruption began with a strong Plinian column, and ended with voluminous pyroclastic flows, an average of 5 centimeters of Plinian ashfall and coinimbrite ashfall covered about 1.5 million square kilometers of the Sea of Japan and northern Japan. This ash layer has been named the Paektu Mountain. It probably occurred in the winter of A.D. 946. This was one of the largest and most violent eruptions in the last 5,000 years, along with the Hatepe eruption of Lake Taupo at around 180 AD, and the 1815 eruption of Tambora. The age of the eruption has not been well constrained. The earliest radiocarbon ages of the carbonized woods yielded 3 different ages: 1050 plus or minus 70 BP, 1120 plus or minus 70 BP, and 1410 plus or minus 80 BP. History of 14C Wigle matching dating. In 1996, Dunlap reported a high-precision Wigle matching age determined at the University of Arizona as 1039 plus or minus 18 AD. However, in 1998, Liu reported a 14C measurements from the center to the edge of the wood, followed by fitting with a high-accuracy tree ring calibrating curve. The obtained age of the Millennium Eruption was determined to be 1215 plus or minus 15 AD. In 2000, Horn reported another Wigle-matched radiocarbon dating with an AMS mass spectrometer, and the interval of highest probability is 969 plus 24 minus 15 AD, which is widely used. In 2000s, at least 5 of high-precision 14C Wigle matching ages had been reported: 930943 AD, 926 plus or minus 10 AD, 945960 AD, 931 plus or minus 10 AD, and 946 plus or minus 06 AD. Recent 14C Wigle matching dating. Zhu et al. Reported 27 best Wigle match datings from a single partially charred 264-year-old tree, which is 946 plus or minus 03 AD. Yin et al. Also reported 82 best Wigle matched AMS 14C ages of samples from 4 carbonized logs, which is 938 939ths. However, the result of Zhu et al. Used a regional 14C offset in their ages to decrease the error, and the new date was obtained from the longer tree ring sequence with the higher analytical precision of plus or minus 25 14C years, on a 260-year tree ring sequence that covers 3 consecutive Wigles around A.D. 910, AD 785, and AD 730. Since longer-dated tree ring sequence, finer sample resolution, and higher 14C analytical precision all facilitate more and tighter tie points for better WM dating, the new date is believed to represent yet the best high-accuracy and high-precision 14C WM chronology for the Millennium Eruption. XU's wood samples were cut from a tree growing in the area about 24 kilometers from the vent of Changbaishan volcano. It is not clear if volcanic CO2 emission before the eruption could affect the samples and produce ages that are slightly too old. The best WM dates for the Millennium Eruption use the outliers removed subset of the original 14C measurements and also account for the effect of possible regional 14C offset, and yielded two nearly identical WM ages of AD 945 plus or minus 3 and AD 947 plus or minus 3, where overall and combined agreement indices of the models reach the highest values. Therefore, the average of these two WM ages represents the best model WM age for the Millennium Eruption. History record. The book described and in 946 AD. Also, the book record on the 3rd of November 946. The thunders may relate to the Millennium Eruption, and white ash rain may relate to trademark ash. 3 months later, on the 7th of February, and were recorded in and another similar record is on the 19th of February 944 in. Based on the historical record, the eruption may have started on February 944 and November 946, reaching a climax in February 947. Ice core Sun et al. Found volcanic glass in Greenland, which could well have originated in the Millennium Eruption magma. The age of volcanic glass layer is 939–940 AD. However, Sigle et al. Found out that ice core chronology is a 7 years offset, and the Millennium Eruption glass layer should be in 946–947 AD. This conclusion is consistent with Wigle matching dating and history records. Eruption volume. The eruption volume has not been well constrained, from 70 to 160 cubic kilometers. Machida et al. Roughly estimated the proximal volume no more than 20 cubic kilometers, and the volume of distal B trademark ashfall attains more than 50 cubic kilometers. A low total bulk volume estimate is 70 cubic kilometers. Horn and Schmink used an exponential method for minimum area thickness and maximum area thickness to obtain the volume of the Plinian ashfall as 82 plus or minus 17 cubic kilometers, and used the area thickness method for ignimbrite to obtain 14.9 plus or minus 2.6 cubic kilometers. The total bulk volume estimate was 96 plus or minus 19 cubic kilometers. Liu et al. Also used same method with Horn and Schmink to calculate the volume of Plinian ashfall, and obtained the similar value of 83 cubic kilometers. However, Liu used a different area thickness value for ignimbrite. Liu assumed a distribution of ignimbrite within 40 kilometers of the caldera, and an average ignimbrite thickness of 7.47 meters, yielding a volume of ignimbrite of 37.5 cubic kilometers. The total bulk volume from this is 120 cubic kilometers. Guo et al. Used the exponential method estimate that volume of ashfall is 135.2 plus or minus 7.8 cubic kilometers. But Guo assumed the geometry of ignimbrite is a cone, and the volume of ignimbrite could be 20.1 cubic kilometers. Guo also calculated the volume of valley ignimbrite, because in a valley the thickness of ignimbrite could be 80 meters. Then, the total bulk volume is 161.6 plus or minus 7.8 cubic kilometers. However, 100 to 120 cubic kilometers has been widely used. Eruption dynamics. Based on the sequence of pyroclastic, the eruption began with pumice and ash falls, and then an eruption column collapse formed ignimbrite. The column collapse probably was a pulsing collapse, because the ignimbrite and pumice fall deposits are interleaved. Machida et al. Divided the Millennium Eruption into 4 stages: Paektu Plinian Pumice Fall, Changbai Pyroclastic Flow, Untitled Falls, and Baishan Pyroclastic Flow. But Baishan Pyroclastic Flow may be related to post-caldera activity. More recent studies indicate that eruption include 2 stages: Plinian Pumice Fall and unwelded ignimbrite. Plinian Stage. This stage formed a large area of white kommanditic pumice and ash. The Plinian eruption column reached about 36 kilometers in height. Trademark ash and white ash rain may be related to this stage. Based on variations of grain size and thickness of pumice, the Plinian stage can be divided into 3 parts: early period, climax, and later period. Early period. In a Plinian pumice fall section, the grain size of pumice is reversely graded. The variation of pumice size shows a major fluctuation in eruption column height during this Plinian event. Based on distribution of maximum lithics clasts in the early eruption column probably reached 28 kilometers. A mass discharge rate attained 108 kilograms per second. Early period may released 1.88 to 5.63 times 1019 joule, and eruption might lasted for 33.5 to 115.5 hours. Climax period. Based on the distribution of crosswind of maximum lithics clasts, the top of eruption column might have reached 36 kilometers, with a mass discharge rate of around 3.6 times 108 kilograms per second. The distribution of downwind of maximum lithics clasts showed the wind direction at the time to be 120 degrees, and the wind speed to be 30 meters per second. The height of eruption column, the water content of magma, and the temperature of magma indicate that radius of the eruption vent was 200 meters. The climax of the eruption may released 4.18 to 12.43 times 1019 joule, and the eruption might lasted for 35 to 104 hours. Later period. This period eruption formed the upper part of the Plinian pumice fall, which is the fine pumice. The later Plinian pumice fall and pyroclastic flow occurred simultaneously, because some sections show that pumice fall and ignimbrite are interleaved. Combining the grain size of pumice and thickness of pumice fall, the height of eruption column of later period was no higher than 14 kilometers, and the mass discharge rate was 5 times 106 kilograms per second. The later period may release 8.76 to 26.16 times 1017 joule for Plinian eruption and keeping eruption column. Ignimbrite stages. In many sections, a large grey ground surge under an ignimbrite sheet, which might be from the front part of pyroclastic flow, and the unwelded ignimbrite always underlay a large ash cloud surge. Ignimbrite was deposited within a 40 km radius of the caldera, at an average thickness of 7.47 meters. In many valleys, the thickness of ignimbrite may be 70 to 80 meters. The Changbaishan ignimbrite has a low aspect ratio of 1.87 times 10⁻⁴. The speed of the initial pyroclastic flow might have been 170 meters per second, and 50 meters per second at 50 kilometers away from the caldera. Duration. The vent radius and H2O content of magma indicate that the average volume discharge rate of the Plinian eruption and ignimbrite was 1 to 3 times 105 cubic meters per second. A total bulk ejecta of 120 cubic kilometers was derived from bulk volumes of pumice fall and ignimbrite of 83 3 cubic kilometers and 37.5 cubic kilometers, respectively. The ignimbrite-forming eruption may lasted 1.5 days to 4 days, while the Plinian eruption may lasted 3 days to 9.5 days. The total duration of the eruption may be 4.5 days to 14 days. Volatile. Plinian volcanic eruptions can inject a large amount of volatiles and aerosols into the atmosphere, leading to climate and environment changes. Chlorine concentrations in the peralkaline from the Millennium Eruption were postulated to have reached up to 2% and an average of 0.44%. The Millennium Eruption was thus thought to have emitted an enormous mass of volatiles into the stratosphere, potentially resulting in a major climatic impact. C.L. McCurry used an electron microprobe to analyze the volatile in glass inclusion of feldspar. McCurry concluded that Millennium Eruption may have released 2,000 Mount Cl. Liu used chromatography to analyze the average of volatile of 5 whole rock samples, and the contents of halogen is 0.08% to 0.11%. A more recent and more detailed study by Horn and Schmink used an ion probe to analyze the average of volatile in 6 of matrix glass and 19 mel inclusions, and the average of content of Cl in melt inclusions and matrix glass were found to be 0.4762% and 0.3853%, respectively. Horn and Schmink concluded that the Millennium Eruption may have released 45 plus or minus 10 mt of Cl. Another author, Guo, who studies petrology and geochemistry, shows the average of contents of Cl in melt inclusions and matrix glass to be 0.45% and 0.33%, respectively. They concluded that Millennium Eruption may have released 109.88 mt of Cl and 15.82 into the stratosphere. The Cl contents in the melt inclusions are similar to those of Mare Island, and higher than those of Tambora, Krakatoa and Pinatubo. The large difference of results between Guo and Horn is because Guo used higher volume and density of magma. Liu used chromatography to analyze the average of volatile of 5 pumice and obsidian, finding the contents of this to be 0.0415%, and Liu assumed the degassing efficiency factor of this is 0.3. Liu estimated that the Millennium Eruption may release 40 mt of SO2. However, Horn and Schmink calculated that only 20% of the sulfur in the magma had been degassed, because 80% of all analyses of inclusions and matrix fall below the detection limit of ion probe. The results of average contents of S in 19 of inclusions are 0.0455%. Horn assumed the contents of S in matrix glass is 0.025% because 250 ppm is detection limit of ion probe. They concluded that the total SO2 release from eruption was only 4 plus or minus 1.2 mt. But Horn suggests that maybe excess sulfur accumulated in vapor phase. Guo calculated the average contents of S in 9 glass inclusions and 1 matrix glass is 0.03% and 0.017%, respectively. The results of Guo are 23.14 mt of SO2 release from eruption and 3.33 mt of SO2 input to stratosphere. The S contents in glass inclusions show the reverse correlation with silicon peroxide concentrations, indicating that S solubility in magma is controlled by magma differentiation process because of occurrence of the S-rich fluid inclusions. Liu used chromatography to analyze the average of volatiles of 5 pumice and obsidian, finding the fluorine content to be 0.0158 to 0. 0.0481%. Horn and Schimink used an ion probe to find an average fluorine content in inclusions of 0.4294%, but F concentrations in matrix glass show a significant bimodal distribution into F-rich and F-poor. In order not to overestimate seen eruptive F loss, they considered this bimodal distribution of F for calculating the volatile difference between matrix glass and melt inclusions. The volatile loss is approximately 300 ppm F for melt inclusion and F-rich matrix glass, whereas it is 1900 ppm F for melt inclusion and F-poor matrix glass. Horn concluded that 42 plus or minus 11 mt of F was released by the eruption. Guo, based on less samples, calculated that F contents in inclusions and matrix glass is 0.42% and 0.21%, respectively. Guo concluded that 196.8 mt of F was released from eruption, with 28.34 mt of F injected into the stratosphere. With magma evolving, halogen contents increase irregularly, parallel to the increase of silicon peroxide concentrations in glass inclusions. The large difference of results between Guo and Horn is because Guo used a higher volume and density of magma, and higher difference contents between matrix glass and inclusions. Vapor phase. Sulfur is not strongly enriched during differentiation, in contrast to water, chlorine, and fluorine. The reason could be pre-syn eruptive degassing of a separate vapor phase, such as that postulated for the Pinatubo and Redoubt eruptions. The ultimate source for the excess volatile observed during the 1991 Pinatubo eruption is assumed to be sulfur-rich basaltic magmas underlying, unsyn eruptively intruded into the overlying felsic magmas. The sulfur-rich trachytic and trachyandesitic magmas which underlay the rheolitic magma at Changbaishan may have been a possible source for excess sulfur accumulation. If this scenario is realistic, clear-cut proxies for the environmental impact of the eruption would be expected. Millennium eruption magmas are predominantly phenocryst porcamendites plus a volumetrically minor late-stage more phenocryst-rich trachyte. Sizable glassy but bubble-bearing melt inclusions are widespread in anorthoclase and Hedenbergite phenocrysts, as well as in rarer quartz and fayalite phenocrysts. Comparing the relative enrichments of incompatible volatile and non-volatile elements in melt inclusions along a liquid line of descent shows decreasing volatile ZR ratios, suggesting the partitioning of volatiles into a fluid phase. This suggests that current gas yield estimates for the Millennium Eruption, based on the petrologic method, could be severe underestimates. Climate effects. The Millennium Eruption was thus thought to have emitted an enormous mass of volatiles into the stratosphere, potentially resulting in a major climatic impact. But more recent studies indicate that the Millennium Eruption of Changbaishan volcano might have limited regional climatic effects, rather than global hemispheric impact as implied by its magnitude. However, there are some temperature and atmospheric anomalies in A.D. 945 to 948 which may relate to the Millennium Eruption.